once again, the technique of what is called Newton's method is a technique to solve equations. And like, think about it, in algebra, you can solve quadratic equations easily, right? There's a formula there. You can solve linear equations easily. There's, you put everything on one side, the variables on the other side, etc. But what happens, excuse me, if you have an equation third degree or higher, or even equations that have like, not necessarily polynomials, but like trigonometric functions and things like that. For example, what if you had something like x cubed minus cosine x equals to 25 or something like this? We have no tools from algebra to solve this, right? Basically, by the time you get beyond quadratic equations, the techniques of algebra are really not very reliable. You have rational zeros theorem, etc., but they're not that good. They're not very efficient, etc. So today we're going to learn a method to solve higher degree equations. It's really amazing, and it's called Newton's method. And you had to know a little bit about calculus before you could study it. That's why we're introducing it at this point in the semester in a calculus class, and you couldn't have known this in an algebra class. So basically, the idea will be the following. We're going to try to solve an equation of the form f of x is equal to 0. Because think about it, every equation can be put in that format, right? You put everything on one side, get 0 on the other side. What does it mean graphically to find the zeros of an equation? What does it mean to solve the equation f of x equals to 0? If you were to graph f of x, how would you pinpoint the zeros? Those would be the x-intercepts, right? So if you have a function, you're trying to solve this equation that is equivalent to saying, find the x-intercepts of that function. So that's what we're going to try to do. We're going to try to find the x-intercepts of a given graph, or that really corresponds to solving the equation. Okay, in the next 10-15 minutes or so, we're going to derive this method by going, you see in your handouts, which is the same as what I have on the board, you have dotted lines. We're going to fill in the blanks. We're going to come up with a formula that will help us to solve equations. And once we have that formula determined, we're going to go and do some examples like the one I have on the top there. We're going to be able to solve these higher level equations. Again, it's really, really important because if you think about it, in a sense, everything in mathematics is an equation, because ultimately, in real life, people are trying to do things. When they're trying to do things, they write it in the form of an equation. So solving equations is such an important concept in mathematics. So this was a huge breakthrough. And again, the credit is given to the mathematician Newton. This is the same Newton with the falling apple, famous in physics. Still, he has also a lot of things, as you can see. He's given the credit, of course, for coming up with the ideas of calculus in the first place. Okay, so here is a general idea. Let's look at this graph. First, I'm going to give you a graphical idea, then we're going to dive into the equations and derive the formula. So let's say you have a function like this. This is your y equals f of x, this curve. And we're trying to solve the equation f of x equals to 0. So that amounts to finding this point right here, correct? The x-intercept. We're trying to find this point. And the way this method works is you begin with an initial guess. Okay? Here our initial guess is x sub 0. You take the initial guess, you plug it into the function. Right there, you draw the tangent line. So right there, you draw the tangent line. Do you notice that the x-intercept of that tangent line is now a little bit closer to the actual 0? So your initial guess was this much apart, right? Your initial guess was how far away from the actual solution, this far away, right? But the x-intercept of the tangent line is now only this far away, right? And then you repeat the method. This is called the method of iterations. You plug the number back into the function. Let me use another color for that one, say green. Okay, so we're going to go back into the function, draw a tangent line right there. And where it hits the x-axis, do you see now that point is a lot closer to the point we're trying to find? What point are we trying to find once again? The 0, the big red dot right there. So every time you draw a tangent line and look at the x-intercept, basically it's getting closer and closer to the original number we're trying to find. So the way this method is going to work, we're going to create a table of values. We're going to create a table of values. This is called iterative method or iterations. So we begin with initial guess. We're going to do something, get something else. Then we put that number in here, and then that's going to give us another number. We keep getting closer and closer to the actual 0. And when do you stop? When do you stop with the method of iterations? When two successive zeros are really, really close. How close? The problem will specify. Let's say you want accuracy to the nearest hundredths. So that means you're going to stop. Like if one solution is 3.99, and the other one is, let's say, you still get like 3.9948, something like this, that they're not changing that much. After a point, you see they're really close to each other, that's when we're going to stop the solution. Now, I actually saw a demonstration of this on the internet recently, so let me see if I can quickly show you that before we go ahead and derive the function. Let's see. So they have an equation here. So they say pick an initial guess. At the moment, you see they pick the initial guess of 5.3. Let's just pick our own initial guess. And how many zeros does this function have? It has 1 here, 1 here, 1 here. And depending on what your initial guess is, you're going to find 1 0 at a time. Okay? So let's pick an initial guess. So I'm going to pick like the number 10. And I'm going to click on draw tangent. Oh, first of all, restart at number 10. You see the line drawn. Okay, draw tangent. So at that point, draw the tangent line. Where the x-intercept of the tangent line is, it goes to the function. So now if I say draw tangent again, at that new point, it's going to draw a tangent line. You see already in 2 iterations, it's found pretty much the 0. You see it says 11.3. If I do it again, draw tangent, 11.37, draw tangent. It didn't change that much anymore. So it's already in 2 iterations, it got the answer. You give me, let's restart. You give me another initial guess. Where should we start? Just I want you to see a few of the drawings to get an idea what's happening here. How about like 1 or something like a smaller number? Say 1. Restart at 1. So it draw the blue line. Draw tangent. So it draws a tangent, and where the tangent crosses the x-axis, at that point, it goes to the function once again. So what is it going to do again? And draw another tangent at that point, and another one after that. Already you see it's at 3.34. If I draw a tangent again, it's already, the x-intercept is so close to that 0. Now it's 3.36, 3.369, it's not changing that much. It's already found a solution. Basically, the values has converged to the actual solution. Okay, so now we're going to do this by finding an equation. What is happening here? We're going to find a formula so we can apply this to all the problems. Yes, a question? And
like on the 1 with the 3, it was below the function. Is that just negative now?
Sure, the function value is negative here.
Right, so let's click it again, it went below it.
Do a tangent.
Yes, it's like right underneath. That would be negative 2.9 something.
No, the x-coordinates here are positive. 0 is right here. The x-coordinates are all positive.
Oh, that's an x-coordinate?
Yes, these are right here. These are like 1, 2, 3, 4, 5, 10. These are the x-coordinates, and they're all positive. But they're getting closer and closer to the 0. But it's a little bit of a luck, as you can see. When you pick your initial guess, it's a little bit of a luck as to which of these zeros you're going to end up finding. But since there are computers used these days, you can quickly pick a lot of initial guesses and quickly comb through, and you can find all of them. But in this class, usually I might give you a suggestion saying, so if you're trying to find this 0, I might say, okay, pick an initial guess close to that 0 so that you're going to end up finding that solution. And like on a test, I might only ask you to find one of the zeros because it's going to be too much work to find all the zeros. Okay. So now we're going to derive our equation. Again, we're going to follow from your handout and fill in the blanks. Okay. So first we're going to pick an initial guess. We're starting right here. First we'll pick an initial guess. In the graph below, what number represents our initial guess? X sub 0. So let's fill in the first blank as X sub 0. We draw a tangent line to the graph of f at which point? Remember, the tangent line was drawn right here. We went to the function. That point is x sub 0 comma what? F of x sub 0. Again, the coordinates here are x sub 0 comma f of x sub 0. Find the x-intercept of the tangent line. So we go down, the blue line goes down. And what is the x-intercept of that tangent line that we just drew, the blue line? X sub 1, right? That's the next iteration. And note that x sub 1 is now closer to the x-intercept than the original initial guess was. Now we'll draw a tangent line to the graph of f at which point? X sub 1 comma f of x sub 1. We call this the x-intercept of this tangent line. We're going to call it, that's the green line. What is the x-intercept of that green line? X sub 2. So you get the idea. Basically, we start with our initial point x sub 0, then we get x sub 1, then we get x sub 2, and we keep getting closer and closer to the actual solution. That is the idea. Okay, so continuing on from our handout, we are looking basically for an equation that will give us x sub 1 once we plug in x sub 0. It'll give us x sub 2 when we plug in x sub 1. So it keeps giving us the next point, basically. It's called the method of iterations. And we're going to repeat it until we get the desired accuracy. But how do we find this equation? That's the dilemma. Let's first form the equation of the tangent line through the point x sub 0 and f of x sub 0 with a slope of f prime of x sub 0, because that would be the equation of this line, this blue line here. First, we're going to try to write the equation of that blue line. And then we'll find the x-intercept of that blue line. Okay, so how do we write the equation of that line? Right, point slope form. So y minus the y coordinate here is going to be f of x sub 0 equals the slope. The slope is the derivative at that point, which is f prime of x sub 0, times x minus something. X minus what? X sub 0, right? That was the x coordinate at that. So the tangent line was like this. And we know what that point is, x sub 0 for x sub 0, so we use that point. Now, we need to find the x-intercept of this line. The x-intercept of this line. As a matter of fact, we know the x-intercept. It's x sub 1, right? When it hits the x-axis, that point was called x sub 1. So what we're going to do is we're going to replace xy with x sub 1 comma 0. In other words, we know that this point is a point on that line, is it not? That x-intercept, x sub 1 comma 0. So in the previous equation, replace x with x sub 1 and y with 0, because we know that is a point on the line. So replace y with 0. And replace x with what? X sub 1. So what I have done, let me use again a different color here. What I have done is instead of x, I put x sub 1. Instead of y, I put 0. Why did I do this? Because I know the point x sub 1 comma 0 is the x-intercept of this tangent line. So I know it's a point on that tangent line. So it must satisfy that equation. So when y is 0 and x is x1, it's a point on the line. It must satisfy this equation. So I substitute them in. And remember, we're looking for an equation now. Basically, if you could tell me what x sub 1 is in terms of x sub 0, that's a huge breakthrough, because from there we can get x sub 2 in terms of x sub 1, and we can do our iterations. So the big step right now is, can we get x sub 1 in terms of x sub 0? Can we have an equation for that? So can we solve basically for x sub 1 here? Okay, to solve for x sub 1, let me first divide both sides by f prime of x sub 0. I want to get rid of that factor there. So let's divide both sides by that. So here you already have negative f of x sub 0, right? I'm dividing both sides by f prime of x sub 0. So what does that leave me with on the right-hand side? You divided both sides by f prime of x sub 0, right? So the first expression there is gone, right? This is gone. So what is left then? X sub 1 minus x sub 0 is left there. Remember, I want to solve for x sub 1 in terms of x sub 0. So there's just one step left. If I want x sub 1 right now, what should I be doing? Add x sub 0 to both sides. So if I'm going to add x sub 0, it goes over here as positive x sub 0. And don't forget there's a minus f of x sub 0 over f prime of x sub 0. Basically, this was the next step in your notes. It said solve for the x sub 1, which I've already done it over here. But in your notes it says, okay, solve for x sub 1, get an equation. Okay, now this gives you x sub 1 in terms of x sub 0. But in your notes I also asked you, in general, can you give me x sub n plus 1 in terms of x sub n? Because if you could do that, then from any point to the next one, you're going to go with ease, okay? So if this is going from x sub 0 to x sub 1, I need to know, and I can even put it right here, what will x sub n plus 1 be in terms of x sub n? Any thoughts? X sub n minus f of x sub n divided by f prime of x sub n. How do we do it? We just looked over here. When you had a 0 subscript on the left side, you had a 1 subscript on the right side, right? So now if you have an n plus 1 subscript on the right-hand side, you're going to have a subscript of n on the left-hand side. So that actually gives you the general formula that we need for the Newton's method. What you see here, ladies and gentlemen, this is it. This is the formula that Newton came up with to solve equations of any order, any degree, even trigonometric, even logarithmic equations. But there is a catch. Unfortunately, there are times when this method doesn't work. It works most of the time, but there are situations where, like there are graphs, something like this. You go to the function, you draw a tangent line, like you get here. Then you go to the function, you draw a tangent line, you get here. So sometimes it goes in a loop. It keeps coming up, like going back and forth, the same tangent line, the same tangent line. It never converges. But this occurs rarely, so this method is still really good. It's not 100% good, but it works in most situations. And after Newton, other mathematicians came by, and they even created better methods than Newton's method. So now there are other iterative methods, which you might take in a class called numerical analysis. Like if you're an engineering major, you may take that class. But in this class, we just look at one basic model, one basic technique to solve equations using iterative techniques.